Good evening, Energy Rogue Nation. Welcome back to another weather discussion. Thank you all so much for tuning in. This is not going to be my typical forecast discussion, although that's how I led the video. A little bit misleading. Instead, we're not going to be focusing in on the tropics tonight. We're not going to be even talking necessarily about short and long-term temperature trends. Instead, what I would like to do is go a little bit more under the hood on the concept of weather models. So, in last week's live stream that I did with Brian and Bill, I talked about my seasonal forecast for both the fall and winter in the United States as we go into the rest of this year, into 2025, and of course I also touched on the tropics, but most of the conversation was geared towards temperatures, right? So I wanted to go a little bit more granular with this because in my live stream discussion, as you all know, I'm not just addressing members of Energy Rogue, but also people that aren't clients of Energy Rogue and ours. So I'm addressing things to a broader audience. I want to just mostly get a broader point across as opposed to getting too under the hood. And so in my live stream discussion that I did, I talked about the climate models such as the CFS and another one called the CANSTIPS, which I did not show, but I'm going to show you here in a moment. And I've told you guys many times about weather models and that they're different and they're not right all the time, hence there's no such thing as a silver bullet. But what I haven't really done is explain the why. Because I know some of you out there that are listening to this are probably thinking, well, Brendan, why is it that we use different weather models, for example? I mean, yeah, you said there's no such thing as a silver bullet in meteorology, but why not just use one as opposed to, say, 7, 20, 30, 40 of them, right? And so I'm going to explain that here in a moment. But this conversation about models is also going to seep into the current discussion that's being had in the Energy Markets channel over on the Energy Rogue Discord. I've seen some very insightful conversation taking place between some of our members regarding how weather is going to impact natural gas as we head into the fall and winter. And there certainly are implications on the natural gas side of things when we're talking about supply and demand, which Brian and Bill can elaborate a lot more about what the situation is with nat gas as a whole, much better than I can. But they did highlight the impact of weather. And also, Cash, you talked about the tropics, right? If we have, say, a hurricane that were to hit the Gulf in September, what role does that play? Especially as we've seen Beryl impact the Freeport LNG site. That has been a complete exposure of terrible infrastructure in Texas, right? That's a whole nother conversation for another day. But the point is, I've seen a lot of talk about the implications of this weather season with respect to the current economic state of the commodity of natural gas. And so my discussion tonight is not going to talk about the nat gas side, more so of the weather. So it's going to be two parts, just to recap. One, we're going to talk briefly about weather models, what makes them different, and then we're going to tie that back into why I'm forecasting the way that I am for the fall and winter season. So, that all in mind, I want to start with this video before I do one last caveat as I think about it. When it comes down to weather model discussions and what we call in meteorology numerical weather prediction, for me to explain every single granular detail would require either several videos of this format or one long 2.5, 3 hour crash course on weather models. I am not going to do that, at least right now. But if you do want some further information on some of these things we talk about tonight, you can feel free to message me on the Discord, and I'm happy to provide further clarification and elaboration. So the thing that we're going to focus on tonight is the essential question of why. Why do we use different weather models? Well, it comes back to the idea of meteorology, right? Meteorology is actually in different scales. So I'm actually going to go ahead. I'm going to zoom out of this page, and I didn't have a notepad up, so I think I'm just going to go ahead and pull one up now. But I want you to think about the atmosphere. But rather than think about all these different layers that we have, I want you to focus more in on the troposphere. And my cat is now making an appearance tonight, ladies and gentlemen. So if you do hear some meowing, he will, of course, be joining us and is also interested in some numerical weather models. Anyhow, our weather takes place between the surface and about 12 kilometers high. In meteorology, we call this the troposphere. So here's 12 kilometers. 0 kilometers is just representing our surface. And with that, there's different heights in between it. We don't just go from 0 to 12. If we're talking about, severe convective storms like, say, supercells and tornadoes, well, that usually works around the 0 to 3 kilometer range, right? And this is what we call in meteorology the boundary layer. Again, you don't need to know all these terms. This is just to give you more of a visual. We're not going to go too granular with that. But the boundary layer exists, we'll call it around 3 kilometers. Above 3 kilometers, when we're starting to talk about our jet stream, that takes place about 5 to 7 kilometers high. And then so on and so on. So all of these different height ranges within this broader troposphere is essentially representative of different scales. So you may see, for example, 0 to 3 kilometers, that's what we call mesoscale. If we're talking about 5 to 7 kilometers, we're looking at synoptic, etc., etc. So you get the point. So why that is important is because when we revert back to our models, right, we really have 3 different approaches. We have one being mesoscale. We have 2 being our, what we call synoptic. And we have 3 being climate. Now, each one of these model types, any one of the weather models we look at, are going to fall into one of 3 of these criteria. In the case of mesoscale, we're typically looking at models such as the rapid refresh, also known as the HRRR. We're also looking at the North American model, and as well as the FV3. I mean, there's several different ones we can look at, guys, but these are just some examples. The synoptic scale, we're looking at models like the GFS and the Euro, which you guys are very well familiar with. And climate is looking more at the CFS and the CANCIPS. So we've categorized our weather models to each of these scales. Each one of these scales are corresponding with different heights within the troposphere, which, as we established, the troposphere, which is a layer within our overall atmosphere here on Earth, is between the surface to about 12 kilometers high, and technically 13-ish, but you get the point. So we're essentially taking where our weather happens and slicing it and dissecting each part, each component. And the same thing works with our weather models. So in the case of the mesoscale, right, if we just focus in on that for a second, we'll erase all this. Look at the mesoscale. We're focused in on these models, the HRRR, the NAM, and the FV3. The purpose of these is to resolve mesoscale features. Now, what does this mean, right? Mesoscale features essentially are talking about our supercells. We're talking about MCSs, or what we know as windstorms. And I do apologize in the background. I have a cat and also a dog. So we will go ahead and shut the door. You can tell this is impromptu. So we have supercells, we have windstorms in the mesoscale. We're resolving for smaller scale features, more localized storms, right? So mesoscale serves the purpose of resolving on a very fine scale what types of thunderstorms we'll see, or how hot and cold will it be for a local region. there are many different components of mesoscale that we can talk about. Again, I'm not going to go into that in detail. This is a crash course on just weather models, just scratching the surface. But mesoscale is referring to smaller scale features in our atmosphere. In this case, localized thunderstorms on the order of about 100 or a couple hundred miles. In the case of synoptic, it's the opposite. We're not so much focused on the small, fine-scale features. We just want to get a better idea of the overall pattern. So with synoptic, we're not focused much on necessarily convective thunderstorms. We're more so focused on larger scale things, such as jet stream features. So our jet stream. Or we're also focused on things like hurricanes. And for the most part, corresponding with jet stream, we're also focused in on just, well, ridges and troughs, which is kind of the same thing as jet stream. So that's technically both, ridges and troughs. So in the case of synoptic weather models, like the GFS and the Euro, we are focused on larger scale features. So as a result, we're not really looking at the granular on our radar, or our weather models in this case. We just want to see what the overall pattern looks like in order to get a general trend of what's to expect. The GFS and the Euro in this case is not meant to resolve the types of severe convective storms we'll see, like derechos and supercells. Instead, it's meant to show you what the setup looks like, what the pattern looks like. And so the synoptic scale is not really meant to give you a fine-tuned answer on temperature, but it does show you the trend, which is why when you look at, say, our website, wxroad.com, you will see that the temperatures at least shows you a trend on our population weights, degree days, or top 5 cities. So it's meant to just give you a big picture look or a broader view of the weather pattern itself. So then that leads to our climate models. And our climate models do kind of the same as synoptic. I mean, they are trying to resolve for a broader pattern, but rather than trying to resolve necessarily the jet stream, which it still does, it's really more focused in on what's called teleconnections. Now, just like what I talked about with the mesoscale, there's a lot that we can dissect here on this topic of teleconnections, and I'm not going to do that here. What I will say, though, is that teleconnections are when we look at El Nino, La Nina, or for my folks in Europe, you guys probably hear this a lot, the NAO, the North Atlantic Oscillation, right, etc., etc. The climate models are meant to look at an even broader picture than what the synoptic scale looks at. It's meant to, rather than just look at the jet stream, say, okay, let's also look at the climatological normals, and let's then forecast out based on current conditions, right? Let's try to forecast out general pattern trends, but more so, rather than looking at the pattern itself, let's look at the teleconnections, El Nino, La Nina, etc. So that's the difference between the three. And just to kind of conclude on that, how does that tie back into this website or what we've talked about? Well, notice how on Tropical Tidbits, we have the models organized in that fashion. We have mesoscale, we have global, which is synoptic, and then we have our climate forecasting, which is here in our climate models. So think of weather models not necessarily as those trying to compete against one another to see who's right. Instead, it's meant to give you the full picture, the full scope of what's going on, from the very top of our troposphere all the way down to our boundary layer from the surface of 3 kilometers with mesoscale. It gives you the full entire picture, right? We drew that diagram, so 12 kilometers, and here's 0, the surface. Well, this suite of models is meant to give you each individual scale, which thereby, when you derive each different kind of slice, gives you the full picture. So, tying back to what I talked about in our discussion this past week, we looked at the climate forecasting model, which is the CFS, and we looked here at this jet stream map, which shows, according to this output, that as we go through the months of September and October, we become more zonal with our jet flow. And as a result, that would imply more milder, but also slightly above normal conditions for a large swath of the lower 48. Now, one thing I didn't talk about much in that discussion, I did briefly, but one thing that I want to elaborate on is a product that I talked about on the live stream, and that is the 2-meter temperature anomalies. Here's the thing. The temperature anomalies shown on this depiction of the CFS, you can see here, for example, in the plains when it comes to October, we see a temperature anomaly of about 1.5 degrees Celsius. So 1.5 degrees Celsius above normal. But if you remember anything that I mentioned in the last 5 to 10 minutes, I just mentioned that with the CFS, one of the limitations that because we're trying to resolve for even broader scale weather features, well, subsequently, it's not going to be telling the full picture with our temperatures, right? As a matter of fact, if we wanted to know more of a fine scale of how warm this will be, or how above normal this will be in some spots, you would have to look at the mesoscale for that. You'd have to look at the HRRR, or the NAM 3 kilometer. The problem with that is we can't do that because these models only go out a few days. They don't go out months, right? So what you'll find with these weather models is that every one is available to you, but they have their limitations. Because in order to resolve for one feature, they have to essentially dissolve for another. Now, it's not to say that the CFS is wrong in these temperature outputs, because these trends have come to fruition in the past. But what we see many times over is that to really get an idea of the warmth, we really won't know that until as we get closer and we have more model guidance available to us. This is a very broad depiction. For example, it's painting a general path of 1.5 degrees Celsius above normals for the plains. But we know for a fact that there is likely to be some places, some localities within these areas that are going to be even warmer than that. It could be 3 degrees above the normals, right? So the important thing I want you to take away from this, and I really did throw the kitchen sink at you guys tonight, and I appreciate you listening in. The thing I want you to take away from this is models help to give us a clearer picture about what we anticipate happening, whether right or wrong. And in order to do that, we have to look at our climate models. We have to look at our mesoscale when we're expecting storms long range and see, okay, what type of storms can we expect? And we also have to tie things in by looking at the GFS and the Euro, our global model, synoptic scale, in order to see what the jet pattern setup looks like. All these different suites of models give us the full scope of our weather. And to use just one of these, or to use just the mesoscale, would be a total sort of lack of observation of other parts that make up our weather. You can't do that. It's very neglectful, right? So I hope you found this video well. If you have any questions, feel free to let me know in the Discord. And I hope that not only did you find it well, but you also found this to be rather informative. So if you want my forecast on the rest of the season, you can check out the live stream on Energy Rogue, the YouTube channel. I talk a lot about my forecast there. I'm going to save that for now because I think I talked a lot about weather models here just now. But hopefully this gives you some clarity as far as why I'm forecasting the way that I am based on these different solutions. I certainly did not go over everything that we need to when it comes to weather models. Again, this is a very surface level discussion. But if you need any clarification, like I said, or you want me to elaborate on some things, feel free to post those down in the Discord below, and I can go a little bit more granular for you guys if you want further clarification. Thank you so much for tuning in, and we will see you on the next weather video. Take care.